Welcome. You want to get up to speed on complex topics quickly, but, without getting totally overwhelmed. That's what we aim for here.
And today, we're looking at a pretty interesting new way to scale up language models.
That's right. We're diving into a paper called Parallel Scaling Law for Language Models. It introduces something called ParScale.
Yes, the material you shared. Our mission, essentially, is to understand this parallel scaling idea, see what the benefits might be, without getting lost in all the super technical jargon.
Okay, let's set the stage a bit. So, traditionally, if you wanted a more powerful language model, you had a couple of main options. You could scale up the parameters, basically make the model bigger, add more connections, but that costs a lot more memory.
Right, a lot more memory.
Or the other way was scaling inference time, just letting the model think longer, run more computations for an answer, which, well, takes more time.
And the paper's introduction really flags these issues, doesn't it? The big memory hit or the time cost that comes with those standard approaches.
So ParScale tries something different. This is the interesting part. Instead of just one bigger model or one model taking longer, it's about parallelism.
Yeah. Imagine taking the input you give the model.
Like a prompt.
Yeah, a prompt or whatever input. And ParScale creates like multiple slightly different versions of that input at the same time.
Okay.
And it feeds all these versions through the same base model simultaneously. Then it combines the outputs from all those parallel runs in a clever way.
So not just running the same thing multiple times, but running variations in parallel.
That's the core concept. Applying these parallel transformations, processing them all at once, and then aggregating the results.
Yeah.
The paper has that figure 1, which sort of sketches this out, multiple streams going in, then coming together at the end.
Okay, I think I get the picture. And the big question they were asking, the hypothesis was, can scaling things this way, this parallel computation, give you the same kind of performance boost as just making the model physically bigger with more parameters?
Yeah, that's the central hypothesis. Can scaling the computation in parallel be an effective alternative to just scaling the size?
Well, how does it actually work? You mentioned these transformations.
Right. It uses what they call P-diverse and learnable transformations on the input. So P is just the number of parallel streams you're running.
Learnable. So the model figures out the best way to transform the input.
Seems like it. It generates these P slightly different takes on the input. Then these all go through parallel forward passes in the same model, just processing P inputs at once.
Okay.
And then, crucially, there's a dynamic aggregation step at the end. It doesn't just, average the P outputs. It intelligently combines them.
And they mentioned this is pretty flexible, like it doesn't rely on one specific model type.
Yeah, they emphasize it can work with different model structures, optimizers, data, tasks. It's presented as a general technique. Again, figure 1.1 helps visualize those streams converging.
Which brings us to maybe the core finding, this new parallel scaling law. What did they discover there?
Well, they found that using P-parallel streams lets a model perform roughly like a model that has significantly more parameters. The relationship they found is logarithmic, specifically O log P.
Logarithmic, so diminishing returns, but still you get gains comparable to adding parameters, but maybe more efficiently.
That's the idea. For you trying to grasp this efficiently, it means potentially big performance jumps without the same massive increase in model size or, as we'll see, inference costs.
Do they give concrete numbers on that efficiency?
They do. Compared to just scaling parameters to get the same performance bump, ParScale apparently needed up to 22 eggs less memory increase and 6 times less latency increase.
Wow, okay, 22 times less memory increase, 6 times less latency. Those are pretty compelling numbers.
Definitely highlights the potential efficiency.
What about the theory? Why does this work? They mentioned something about classifier-free guidance.
Yeah, they draw inspiration from CFG. The intuition, maybe simplifying a bit, is that CFG works by sort of nudging the model's output based on different conditions. ParScale seems to tap into a similar idea, getting multiple perspectives from these parallel streams and combining them.
Like getting slightly different angles on the problem.
Kind of. The paper has equation 4, and it brings up this concept of diversity between the parallel streams.
Diversity. So the transformations need to be genuinely different.
That seems key. The theory suggests that if the streams are more diverse, offering distinct viewpoints, the final combined output is better. More diversity leads to better performance. It might even offer some insight into why CFG itself is effective.
Makes sense. Did they test this out properly?
Oh, yeah. They ran large-scale pre-training experiments. We're talking 42 billion tokens using the StackV2 and Pile datasets.
Big data sets. And did the results match this scaling law they proposed?
They did. Figure 1-2 shows the fitted law against their experimental data, and they reported high R-squared values. That's a statistical measure of how well the line fits the data points.
So, good fit. The law seems to hold up in practice.
Seems so. And they confirmed that logarithmic trend as you increase P, the number of streams, the performance improves, but the gains per added stream get smaller.
Okay, and you mentioned two data sets, Stack V2 and Pile. Did ParScale work equally well on both?
That's an interesting point. They found the K value, which sort of measures how much benefit you get from the parallel computation, was higher for Stack V2.
Stack V2. That's the coding and reasoning one, right? Pile is more general knowledge.
Correct. Stack V2 is more coding reasoning focused. Pile is more about broad knowledge, maybe memorization.
So ParScale helped more on the reasoning data set. What does that suggest?
Well, the potential implication is that this parallel computation approach might be particularly good at boosting skills related to reasoning or complex problem solving, maybe more so than just pure memorization.
Huh. So computation for reasoning, parameters for memory, maybe.
It's a possible interpretation they raise. And the downstream task results in tables 2 and 3 seem to back this up. They saw performance improve with more parallel streams, especially on coding tasks.
Right. Now let's talk about actually using these models. Inference cost. Memory and latency are huge there, especially if you're not running on massive servers.
Absolutely. Critical for low resource scenarios.
So how does ParScale compare on that front? You mentioned those earlier numbers.
Figure 4 dives into this. It essentially shows that to reach a certain performance level, ParScale increases memory usage and latency much less dramatically than just making the model bigger via parameters.
Less memory, less waiting time for the answer for the same quality.
That's the finding, especially at smaller batch sizes, which are typical for things like phones or maybe smart devices in cars.
So this could really help get powerful AI onto, edge devices. Things without huge computing power.
That's definitely one of the potential benefits they highlight. More capability without the prohibitive resource costs.
But what about training? Running P streams sounds like it could be expensive to train in the first place.
That's a fair point. Training could be costly. So they proposed a two-stage training approach to mitigate this.
Okay, how does that work?
The idea is, first, you do standard pre-training on a really large data set, the usual way. Then you take that pre-trained model and do a second stage of training using ParScale, but only on a smaller amount of data.
So you don't need to run the parallel stuff on the entire massive training set.
Seems to be the idea. Figure 5 shows the loss curve, how well the model is learning. There's a little bump when ParScale starts, but the model adapts quickly.
Does it still perform well? Training on less data with ParScale in the second stage.
Apparently, yes. Table 4 shows results even when they trained on a huge 1 trillion token dataset using this two-stage method. They still got significant downstream performance gains, particularly, again, on those reasoning-heavy tasks.
Interesting. And can you apply this to models that already exist, or do you have to train from scratch with ParScale in mind?
Good question. They tested this too using an existing model called Qwen 2.5.
Right.
And they showed you can apply ParScale afterwards. They did it through continued pre-training, just carrying on the training using ParScale, and also using PIFT.
Parameter-efficient fine-tuning. So adapting the existing model without retraining everything.
That's right. Figure 6 shows these results. It suggests ParScale isn't just for new models. You can integrate it with ones already out there.
And does that lead to this idea of dynamic parallel scaling?
Yes. Since the underlying base model doesn't necessarily change when you apply ParScale, you could potentially change the number of parallel streams you use at deployment time.
Without retraining?
Without retraining the base model, yeah. So you could maybe use fewer streams if you need a quick answer, or more streams if you need higher quality and have a bit more time or compute. Adds flexibility.
Okay, let's try and wrap this up. The key takeaway seems to be that ParScale offers a different way to scale language models, focusing on parallel computation rather than just size.
Right. And it seems to be much more efficient during inference when you're actually using the model, delivering performance gains similar to larger models, but with significantly lower memory and latency costs.
Which, as we discussed, could be really important for getting powerful AI into more places, especially those with limited resources.
It potentially broadens where and how these advanced models can be deployed.
So here's something to think about, building on all this. Considering ParScale lets us get this high performance with less memory and less waiting time at inference, how might that change the whole picture of AI accessibility? Getting AI on all sorts of different devices and into different applications, how fundamental could that shift be?
That's a really interesting question to ponder. The potential downstream impact is quite significant.
Definitely something to keep an eye on. And for anyone who wants to dig into the technical specifics, the paper includes links to the code and the models they trained.